In this lesson, we're asking what angle relationships are formed when lines intersect. And we've seen from the angle addition postulate that when we have two adjacent angles, their measures sum to the measure of the larger angle they create. Well, let's see what happens when they create a straight angle and what we can say about it.
Linear pairs consist of two adjacent angles whose non-common side are opposite rays. Now in this diagram, I see a line with two opposite rays, ray BA and ray BC. Together, they form a straight line, which we can also think of as being at a 180-degree angle, otherwise known as a linear or straight angle. If I wanted to make a linear pair here, what I'm going to need is another ray. Now, I only have two adjacent angles, ABE and EBC, and they form a linear pair because together they make up a straight angle we started with. Now, I want to point out too that a linear pair must only have two angles in it, which means that if I had drawn another ray, I'd have three adjacent angles that make up a straight angle. But they wouldn't be a linear pair because the word pair means two. Now, when two lines intersect, they create a number of linear pairs. And we're going to identify some of them here. ABD and DBC make up a linear pair that you can see in the diagram. Now, if we start with ABE, can you identify any of the angles which make up a pair with it? Well, if you said that angle ABD pairs up with ABE, then you'd be correct. Because this angle right here, ABD and ABE, make a linear pair. Now, if we want to start with DBC, right here, I can see that angle CBE make a linear pair with that angle.
So far, we've learned about linear pairs. We learned that they're adjacent angles that form a straight angle. Next, we're going to learn about a different concept called vertical angles. These are angles which are opposite to each other, which means that they're non-adjacent, and they're formed by two intersecting lines. If we look at this diagram here, we can see two intersecting lines, and two intersecting lines will form two pairs of vertical angles. I've already got us started identifying those two pairs. One pair is with CAB in it, and the other angle that's opposite to CAB is the angle that's opposite that intersection point. That's angle DAE. And we can write this as our vertical angles, and this is the abbreviation that you'll be using when you work through problems on your own. The other pair of vertical angles comes from considering angle CAD. The angle that's opposite to that one is angle BAE, right here. So this pair of angles are vertical angles. This concept is different than the concept of linear pairs because linear pairs must be adjacent. And we see that if angles are opposite, they cannot possibly be adjacent. So let's see now if we can try to identify some vertical angles in this diagram right here. So we're asked to identify the vertical angles, and we have two intersecting lines, so we know that we're going to have some. There's one other thing, though, in this diagram, and it's this ray, and it might cause a little bit of trouble. So let's see what we can do here. One pair of vertical angles that I see right off the bat are angles CAB along with angle EAF. That's these angles right here. Now, those are vertical angles because they're opposite each other. There's only one other pair of vertical angles in this diagram. It's angle BAF along with the angle that's opposite to BAF. And if you look closely at this diagram, you might be tempted to say, well, maybe CAD or DAE is the other angle in this pair. But that'd be incorrect. We want to get the entire angle here, CAE, in order to have a vertical pair. And in this diagram, these are the only two pairs of vertical angles. So what you can do now is try to practice identifying vertical angles on your own. The vertical angles theorem tells us something about vertical angles. It says that if two angles are vertical, then they're congruent. This is a really common theorem to use in geometry. So I'm going to set up some vertical angles here by intersecting two lines. And now we can identify that we have some vertical angles. Here's a pair of vertical angles, and here's another pair of vertical angles. The thing that this theorem is telling us is that these pairs are congruent, or the angles in them, rather, are congruent. So those angles are congruent. I can mark them with congruency marks. And then the other angle pair, which I'll mark with their own congruency marks because they're also congruent to each other. Let's prove the vertical angles theorem. Here we're given that angles 1 and 3 are vertical angles, and we can also see that because they're formed by two intersecting lines. Here we're using numbers to denote the angles because it's going to make our proof a little easier to read. So let's begin our two-column proof by taking the given information that angles 1 and 3 are vertical angles, and we'll say that it's given. Remember that we're aiming to prove that angle 1 is congruent to angle 3. Well, we're going to begin by noticing that angles 1 and 2 form a linear pair because they're adjacent angles with a common ray that form a straight line. So this is really by the definition of a linear pair. Now, we also know that since they're a linear pair, their measures must sum to 180 degrees by the angle addition postulate. And then furthermore, if we look at this diagram, we can see that angles 2 and 3 form a linear pair. Once again, that's because they form a straight line, the two angles together, and that's the definition of a linear pair. So in step 5, we can once again say that we have two angles summing up to 180 degrees, except this time it's angles 2 and 3. Now, if you look closely at steps 3 and 5, you'll notice that you have two sums on the left, and on the right, they both equal 180 degrees. That means that those two sums, they must actually equal each other. So we can say that, let's clear away these markings, we can say that the sum of the measure of angle 1 plus the measure of angle 2 is equal to the measure of angle 2 plus the measure of angle 3. They both equal 180 degrees. And what we're doing here is using the substitution property, along with steps 3 and 5. Now, after we've done this, if you look very closely at step 6, you'll notice that we have the measure of angle 2 on both sides of that equation. So what we can do is use the subtraction property and eliminate it. And that gives us that the measure of 1 equals the measure of angle 3. And now we're really close to proving our theorem because we just need to use the definition of congruence to conclude that angle 1 is congruent to angle 3. And this is, in fact, what we wanted to prove. We wanted to prove that vertical angles are congruent. So this concludes our proof. The vertical angles theorem can help us to solve some questions. And right here, we're going to answer this question. It asks us, can we find all of the other angle measures using properties of linear pairs and vertical angles? Let's see if we can do it. Here we're given that one of the angles in this diagram has a 54-degree measure. That tells me right off the bat that angle 3 must have a 54-degree measure because it's vertical to that 54-degree angle. And therefore it's congruent, which means their measures must be equal. Now we can use what we know about linear pairs of angles to find the remaining angles. For example, angle 4 and 3, well, I know that the measure of angle 4 plus the measure of angle 3 must equal 180 degrees. And I know that because those two adjacent angles are forming a straight angle. I just found the measure of angle 3. We said that it's 54 degrees, so I'm going to erase it out of that expression and just go ahead and write its measure, 54 degrees. Now I can solve for the measure of angle 4. That gives me 180 degrees minus 54 degrees, and when you take that difference, you get 126 degrees. So let's write that in the diagram. The last angle to find is angle 2. It's vertical to angle 4, which means it's congruent to angle 4, and therefore it has the same measure. So I know that this must also be a 126 degree angle. We've been asking what angle relationships are formed when lines intersect. And we've learned about linear pairs and vertical angles. We've seen that linear pairs, well, that their angle measures sum to 180 degrees and that vertical angles are congruent. Next, let's see what types of problems we can solve with this information. Let's solve a problem using what we know about linear pairs. Here we're told that the measure of angle AEB is 147 degrees. Then we're asked to find the measure of angle BEC. I see that those two angles form a linear pair because they are adjacent angles that form a straight angle. To solve this problem, at the start, I'm going to label these angles as 1 and 2. That's going to make the equation a little easier to write. And I said I'm going to use an equation here because in a linear pair, I know that the measures of the angles, measure of angle 1 and the measure of angle 2, must be 180 degrees because they form a straight angle. And that's the definition of a straight angle. We're also told that the measure of angle 1 is equal to 147 degrees. So I can come into my equation and replace measure of angle 1 by 147. At this point, I can subtract 147 from both sides, and that'll give me that the measure of angle 2 equals 180 minus 147. That is equal to 33. So we see that the measure of angle 2 is 33 degrees. Let's see how we could use this type of reasoning to solve a more complicated problem. Here, we're given a linear pair, right here, DHE and EHF, and we're asked to find their numerical measures. The thing is that their measures are given in terms of expressions involving an unknown variable x. Let's start off just like before by giving these angles numerical names, 1 and 2, and then we'll use the fact that they form a linear pair, which means that the measure of angle 1 plus the measure of angle 2 is equal to 180 degrees. At this point, what I'm going to do is substitute those expressions in. So I see that 2x is the measure of angle 1 plus 3x plus 5. And now I can solve this equation just like I would in algebra. I'll combine like terms. That gives me that 5x plus 5 equals 180. Subtracting 5 from both sides, I see 5x is equal to 175. Then dividing both sides by 5 reveals that x equals 35. What we want to do next is take our value for x and substitute it into the expressions for the measure of angle 1 and the measure of angle 2. When I substitute that into the first expression, 2 times x, that's 2 times 35, and that's equal to 70. On the next expression, I will go 3 times 35 plus 5, and I'll see that that is equal to 110 degrees. One other way that I could have done this problem was by using the fact that they're linear angles and subtracting 70 from 180 to get 110 for the measure of angle 2. Let's use what we know about vertical angles to find some unknown angle measures. This problem gives me 2 vertical angles, and it also gives me expressions for their measures and then asks me to find their numerical measures. To solve this problem, I'm going to draw a picture of the situation. I know that I have 2 vertical angles, so I want intersecting lines. So let's label these angles. So one of them is A, B, C, and then the other part of this pair of vertical angles is D, B, So let's make sure we know these are lines, and then we'll write the expressions right here on the diagram. So that would be 5x plus 1, and then the other one has measure equal to x plus 5 degrees. Since those angles are vertical, they're congruent to each other. And we know that congruent angles have equal measures. That tells me that 5x plus 1 must be equal to x plus 5, which is a fact that allows me to solve for x. I'll do that. First off, I could subtract 1 from both sides. That gives me that 5x is equal to x plus 4. And now I could subtract x from both sides to discover that 4x is equal to 4. Finally, using the division property of equality, I would discover that x is equal to 1. That just tells me x. We need to find the measures of those angles. So the measure of angle, let's see, ABC, well, that's going to be equal to 5 times 1 plus 1, which is equal to 6. And using what we already know about vertical angles, I know that the measure of the other angle, DBE, must have the same exact measure, must be equal. So both of these are equal to 6 degrees. There's one last thing that's very important here. And you notice that I just drew any diagram without any regard to the measures of these angles. And we actually found that the angle measures here are only 6 degrees. The reason that that's okay is because when you use diagrams in geometry, you only use the given information. On this diagram, the only given information are these angle measures and the fact that we have some vertical angles and perhaps other angle types. But the measures of the angles in numbers isn't given until we solved for it.